Hi, let's continue with error propagation. This time we'll talk about multiplication and division. If you remember last time when we talked about subtraction and addition in error propagation, the way that we do is all the same, no matter it's plus or minus. Here is the same idea. No matter you do multiplication or division within the number, it doesn't really matter. So you simply do the same thing. So here is an example. If y, which is, it could be anything, is calculated by a times b divide c, you do the same thing. So the formula is actually delta y over y, which is the fractional uncertainty, if you remember in the previous video when we do the definition, equals to each of these. Okay, so I'll say again, because y is equal to a times b divide c, so the uncertainty of this whole thing, y, would equals to the fractional uncertainty of a, fractional uncertainty of b, and fractional uncertainty of c add together. Once again, doesn't matter whether they are multiply or divide, you just add them together. However, since you know I just said it is fractional uncertainty, do you know that there's an issue with the notation here? I'll give you 5 seconds to think about it. So the problem with this formula in the data booklet is, as I said, is fractional uncertainty, so it should be delta y over y log. Because when you refer to y, it will be the whole thing, which is something plus or minus something, right? So that would be y log plus or minus delta y. But then you don't want to do this. I mean, this is nothing. So you should actually write it as delta y over y log, and same for the right hand side as well. So that would be delta a over a log plus delta b over b log, delta c over c log. Once again, if you don't know what I'm talking about, maybe you have to revisit the textbook here, or like what I said in the last video, the notation, right, is very important for us to understand. And this is the standardized notation. You should simply follow that. Otherwise, you have to define, write a lot of stuff, then that will take up so much time. All right, it's meaningless. So let's just follow the tradition that a log, the one with the log, is the average value or the mean value, and delta something is the absolute uncertainty. So that's why I said in the previous video that for sure that data booklet would be useful in your exam for a certain time. But then you also need to know the limitation and some tiny issue with the data booklet. There are some imperfection in it. So if you have your data booklet, I'll recommend you to correct it. I mean, not correct it, but then to put a star or something to remind yourself that this is not perfectly correct. So when you do it in the exam, you should pay attention to this. So let me show you an example so that you know how we can apply the formula just now. So here we have got a rectangle and we want to find the area. So just the two dimensions multiplied together. So the two will be A and B here with its average value and also uncertainty. So the first thing that I will probably write whenever I deal with this question is I write the general formula first, because this time the question didn't tell you. Yes, I know it's very clear, but then I'll still write it just to reiterate what we can do with the physical relationship. So at the end, remember our objective, so I'll write down here that you want to find area A. And in this case, again, it's not primary maths, right? We are doing in IB physics. We are trying to do the error propagation. So we want to express the answer A in A log plus or minus delta A. So we have to find each of these. And so since this is the equation, then a log will equals to, the big A log will equals to the small a log times b log, and that should equal to 2.5. You just look at this number and this number, because these two will be a log and b log, times 5.0, and this should give you 0.75, I think. No, 12.5. Sorry, I don't know why I'm thinking that. Alright, and so for delta A, we cannot calculate it directly. We have to use the formula we just learned, which involves delta A, but then you also have A log down there. Remember there's a log here, not to follow the data booklet one. This is a more standardized way of doing it. So delta, because this is multiply these two things together, so we'll have the small a log, delta small a over a log plus delta b over b log. Okay, and so what we have to do is just to substitute whatever you know here, and I think the only thing unknown is delta big A. So we can keep, actually I should put it up, but never mind. Then A log we know is 12.5, delta A is 0.1 over A log 2.5 plus 0.1 over 5.0. Okay, so then you can just use your calculator to find out the answer, delta big A. So that will be 0.75. Okay, so that means the final answer that you should express here would be 12.5 plus or minus 0.75. Some issue here arise is that we haven't mentioned before, is when you express the uncertainty, absolute uncertainty, our convention is we only express it with one sig fig only. Okay, because the main rationale briefly is that since you are not even sure about these digits, then we usually would not care about the next decimal place as well. So usually we'll just do one sig fig, which will run this up to 0.8. Alright, and 0.8 actually match with the decimal place of 12.5 because this is the only one decimal place you have. So this will be the way that we usually would end up with, and so this will be the final answer, cm cubed. Okay, and there is only one situation where we may consider to keep the absolute uncertainty to be 2 sig fig. That will be something to do with in a situation where you have 0.1 something, right, or whatever that is start with 1. The main reason is that because in this case, so let's say it is 0.14, let's say, then we will just keep it at 0.14. It's okay to keep that, other than changing it to 0.1. Or you can do, say when you have 0.116, then you can round up to 0.2, but then we'll probably keep it as 1/6. I think the main reason behind is, if you do this, then you kind of having a big percentage change in terms of the absolute uncertainty. Because if you think about changing from this to this is about 40% of change, right? And changing this to this will be quite a lot as well. So therefore we would not, it is negotiable that we can keep this number as it is, alright, with 2 sig fig. Of course, if you have 3 sig fig and 4 sig fig, let's say 0.14, 3.2 or etc., we'll still do 2 sig fig at most. But then most of the time we'll do 1 sig fig only for the absolute uncertainty. Okay, this one it may sound quite confusing to you because this has actually no standardized way of doing it. In fact, the error propagation or error analysis will require much more advanced physics when you use it for the physics in the university. The way that you learn right now in high school is a more simplified version. So what we want you to learn the most ultimately is you have the appreciation towards the absolute uncertainty or the error propagation itself. Whether or not it is perfectly accurate, in fact, we all know this is not an accurate method anyway, because this is not the actual way that we should do. It's approximations. So that's why we come up with such a rule for you to follow. Hopefully you get to know about errors and how we propagate. At the same time, when you do your IA, your prediction or the tolerance will be sufficient enough to make your IA meaningful. Before we move on to the next question, let's try to use a more intuitive approach to attempt this question. So what we can think of is, again, the worst case of the area here. So think about a rectangle. What is the worst case? Worst case as in, again, when you calculate the so-called range of area, you have the maximum and minimum here. So let's take a look of how directly if you try to calculate the so-called maximum and minimum, how it will look like. So for say A and B like this here, the maximum of A could be 2.6, right? And then 2.6 here. And so the also the worst case for the big area A will be 5.1. Both of them will be big in order to make it the biggest, right, for the area. So that in that case, the so-called A max would then be 2.6 times 5.1 equals to 13.26, and then A min would well, I guess you can guess now, it will be 2.4 times what? 4.9. That should equal to 11.76, right, with the unit. So if you compare this answer with the one we calculate using the formula, it should be a good approximation, right? It may not be exactly the same. Let's take a look. The one that we find out from the answer here is 12.5 plus or minus 0.8, so I just copy here. This actually means the range of A would be, according to this, would be 13.3, or actually I can do it 11.7, right? So I hope you can understand and appreciate that this is close enough, really. Because if you look at 11.7, this is basically 11.7. In fact, 11.7 is even more. I mean, a little bit more, but I guess it's fine. And so for this one is 13.3, and this one is 13.26. So since we take up to one decimal place at the end because of the issue that we talked about earlier, that one sig fig issue, and so the result actually will match. So hopefully when you are using this equation, you can now feel comfortable to use it. If you are really thinking, hey, Mr. Wong, you are just showing us a special case, right? Like in this example only. Can I just prove it with a more general math approach, like putting a general variable in it without inputting any numbers instead? And I would say I can't do it for you now, because if you really want to prove the equation you learned in the data booklet here, well, for the first one, it's just very straightforward. You just add them together, right? So it's no, you can't even say there's any derived work at all. But then for this one, actually it involves something called partial differentiation, which you won't even learn it in high school mathematics, even in Excel physics. I mean Excel mathematics. If you're really interested, you can go and check out the link I post in the description below. Enjoy the mathematics. Alright, so the next example that I would like to show you is involving kinetic energy. So let's just recall kinetic energy equation is half mv squared. And we haven't talked about how we can deal with square or any kind of index in our case here. So before I do this question, I would like you to change your focus to another equation you can find in the data booklet. So this is one thing that you can find below in the data booklet, which actually is here, okay? And so I want you to spend some time to think about how you can prove this equation. You can actually do that, trust me. Pause the video, try it now.
A few moments later.
Alright, so you can prove this equation by using the equation that we just learned earlier for multiplication and division. And firstly, you also need to understand that y equal to a to the power of n, according to what you learned in primary, it actually means a times a times a times itself for n times. Okay, so imagine these A are not really A, but A, B, C, D, E, F, whatever, like for n different letters. Then it's all the same, because according to what we learned, then we can deduce that delta y, according to the equation that you learned earlier, y log equals to delta A over A log, delta A over A log, and continue delta A over A log for n times. Okay, not to be confused, these are multiplied, these are plus. Okay, so at the end, then you can deduce this into n times delta A, because there are n times of these add together, A over A log. Okay, but then if you look at the equation provided by the data booklet, here you see there's an absolute value. The reason that we have an absolute value is because even if n is a negative value, for example, this is negative 3, then actually it means is y equal to 1 over a to the power of 3. If you remember what I said earlier, no matter you are multiplying or dividing, it's all the same. You always do plus here. So that's why it doesn't really matter n is positive or negative. Even if n is somewhat a fraction, for example, when you do square roots in your equation, you may have the power of 1 over 2. It also works, trust me. So we can go back to the kinetic energy, that question, and I will give you some time, pause the video, try it out yourself, and we'll discuss it together.
2,000 years later.
Okay, so we'll do the way that we do usually. So delta EK over EK kinetic energy log will equals to, actually I should do the log first. Alright, so that will be half m log v log square. I will insist that you should write the general equation first. So then that will be half m log is 4.4, and also you should show the substitution as well. And v log will be 18, so 18 square, the units kg meter, yeah, these are all SI units, so good to go. So then your final answer, I mean not final answer, the log value, okay, 712.8 joule. And then you can move on to calculate the uncertainty by using the equation again. Ignore the 1 over 2 because it's not something that you measure in the experiment. So you start with delta m over m log. And then you could actually think about this v is v times v here. Alright, so then you can have delta v over v log plus delta v over v log, right, which end up with the equation we just proved. Of course, I will do this way because I'm lazy. Okay, so the next thing is just substitution. So you keep here, and then the answer you get, you should be still using the full number by now. Okay, and then you use your calculator to find out the answer. That will be 111.6 joule. So finally, we prepared these two dishes, and let's just put them together. So 712.8 plus or minus 111.6. So once again, according to what we talked about earlier, for the absolute uncertainty, this one, you could either express it with 1 sig fig or 2 sig fig at most, right? And this one start with 1, so you could choose 2 sig fig if you think 1 sig fig is just too much. So 1 sig fig, I'll show you how, because this will become 100, right? So that will be 1 times 10 to the power of 2, right? To show a better, no, actually I should show it as 0.1 times 10 to the power of 3, right? Because it's 100. Yeah, so I think this way is better to fit the scientific notation. And so for this one will be 0.7 times 10 to the power of 3 in this case. Yeah, so that would be the way you want to do it if it is 1 sig fig. Or, okay, or you can also do 2 sig fig. And so in this case, that will be 110, so 1.1 times 10 to the power of 2. And so this one will become 7.1 times 10 to the power of 2 as well. Alright, so then 2 of the decimal place would match, or the digit would match. And so the unit will be joule, and these two could be the answer.